Close. Okay, let's hope that it's better now. Okay, so of course you know that AI is not new. It started back in the 50s, and in fact, some people say that it was Alan Turing that was the first one that planted the seed of AI. This is just an evolution of it. I just wanted to draw your attention a little bit to this period over here, between 1970 and 1990, which is very, very aptly, I think, called the AI winter, because nothing was happening, or at least it seemed that nothing was happening in AI. But why was that? Any suggestions? Yes?
Maybe because there was the Cold War, and each country didn't want to publicize the results, thinking that the other country may. Because we put people in the moon, there is no chance that there wasn't some computer development happening behind the scenes.
Computer development was happening, but if you go in particular in AI, this may be one of the reasons. Perhaps, I don't know, but I think that
But then it starts computational problems with data.
That was another.
More because you have
Indeed.
question,
Indeed.
but also with the data, so
That's also another reason. I think that some kind of consensus has been reached that this was an AI winter because AI promised too much before the 70s, and it didn't deliver. If you remember, automatic translation was a promise of AI even in the early 80s. It didn't work. They used the well-known experiment of translating, actually I think it was a military manual from Russian to English, and then translating it back from English to Russian, and the result was something that was relevant to vodka. So it wasn't that successful at the time. And then, of course, it came back in the 90s. I'm not suggesting that we will live yet another AI winter, but we should be cautious of when the technology promises too much and then it doesn't deliver. There is this long period. Actually, it was 20 years. It's worthwhile, right? It's considerable. So just keep that in mind. We'll come back to this possibly later. Now, 3 ways in which AI, machine learning, and cybersecurity relate. I've already covered this in the agenda. It is used to improve defensive cybersecurity, so for our defenses, but it can also be used, and it has been used, to improve the offensive cybersecurity, so improving the attacker's capabilities. And then the other way around, cybersecurity is used to defend AI systems from cyber attacks. So let's start with the first one.
Yes, sir.
Yes?
Can we first case when AI is object for attacks?
You mean yes, well, actually, this is the last one. This is the third. This is the third. Are we having another crash? No? No, okay, oops. No, that went too much. So these are some use cases. This is not exhaustive. But there are some use cases of using AI for defensive cybersecurity. Of course, the first thing that usually comes to mind, or at least comes to my mind, because I receive every week dozens of papers applying machine learning for intrusion detection. 99% of them are rejected. And I'll tell you why. But this is the most well-known application. The main reason is that when you test these things in the laboratory, you get accuracy rates of 99%, 98%, nothing less than 97%. But if you try those into a real-world experiment, you seldom get anything above 60%. Simple as that. And there are many reasons for this, of course. This is one of the reasons why, if you look at commercial products for intrusion detection, you will not find many using artificial intelligence. Actually, from the most well-used ones, I think it is only the what was called BRO a few years ago. Now the name has changed, of course. That is using some form of artificial intelligence, but not alone. Actually, it is using statistics, and then there is one component that complements that by using machine learning. But anyway, then an extension, detection of malicious objects, for example, infected PDFs or phishing websites and so on. Defenses against denial of service attacks. This is another also thing that needs to be pointed out, that many people design defenses against particular types of attacks. This is not very helpful because, of course, a system is not facing only one type of attack, it's facing many types of attacks, and therefore designing a defense which is good for only one type of attack doesn't help much, particularly because if you complement that with other solutions, usually the result is that the overall efficiency of the system of the defense system is degraded. Then detection of anomalous or malicious activities. This is actually a subset of intrusion detection. Support for digital forensics, identification of fake and compromised accounts in the online social networks. Same for employee accounts. Threat intelligence, actually, this is a very successful application of machine learning, particularly when it comes to leveraging machine learning for understanding, for acquiring, processing, and understanding unstructured information about threat intelligence, like, for example, from online social networks, right? For example, but other sources as well. Then decision support systems and recommenders for SOCs, for sets, and all the other acronyms there. For authentication, extensively used for context-based authentication and also for biometrics, even though, again, there we do know of several biometrics attacks, several attacks against biometric systems that use machine learning. And finally, for vulnerability detection. Lately, there are some applications of machine learning for doing cryptanalysis of cryptographic algorithms. Actually, of course, you don't use machine learning for actually doing the cryptanalysis, but for guiding the process of cryptanalyzing in a more efficient way. Now, so this is a wide range of applications, right? But just a few challenges to close this chapter of machine learning in defensive cybersecurity. We will come back to the intrusion detection issue later on. So we do have high precision requirements in many cybersecurity applications. One example of this is to have very low false positive rates in detection. And this is one of the biggest problems we have in intrusion detection, high false positive rates. Then, to be fair, when you try to assess the performance of a machine learning-based intrusion detection system or anomaly-based system, to compare it against traditional, let's say, ways of detecting anomalies, this might not be absolutely fair using the usual metrics of accuracy, of false positives, of false negatives, and so on and so forth. The reason being that usually the machine learning system is part of an overall system. It's part of a bigger system. And therefore, what should be measured is the performance of the overall system rather than just the machine learning component within the system. And that means that we might need to come up with different metrics. Okay, and I already mentioned the last challenge, that in real world conditions, unfortunately, machine learning based IDSs do not really perform very well. Then next point on offensive cybersecurity. Well, there are bad guys as well. And unfortunately, as every technology can be used for a good purpose, this technology can be used for a bad purpose as well. So we do have several publications in the literature, and I'm absolutely sure that there are many more in the dark literature of how to leverage machine learning to improve the attacker's capability. And in a nutshell, what ML can be used for is to make the cyber attacks more effective, more targeted, cheaper, faster, more autonomous, and more difficult to attribute, and more interactive. Particular emphasis has been put lately on reinforcement learning. This is being used extensively for improving attack capabilities. And there are some examples of use cases. Usage of AI for evading authentication controls. This is a very trivial application to fool CAPTCHA tests. This is why actually CAPTCHA tests have been trying to evolve so as to avoid this kind of situation. Autonomous and automatic movement in cyber attacks. In fact, one of our PhD students has worked on using reinforcement learning for improving attack capabilities against swarms of drones, autonomous drones. Enhanced social engineering, of course, and identity theft, then massive spear phishing attacks, but highly targeted, and interactive and scalable social engineering attacks. All these are available in the literature. This is just one, I would say, crude classification. And the PhD student that I just mentioned to you, actually in her thesis, has come up with a modified cyber kill chain to represent the use of AI in the different phases of the cyber kill chain. I will not go through the details of this picture here, but what you can see is that in all phases of the cyber kill chain, this is not the industrial control systems cyber kill chain, it's the, let's say, simple cyber kill chain. In every one of the stages or the phases, there is a component that can be made more efficient or can be supported by AI. And as I said, the details are there, and of course the reference is there if you want to go through it. Okay, so now this is how machine learning or AI. Again. Something funny happens when I use the laser pointer and then I try to advance the slide. Okay. Well, it needed the master. So, yes. Okay. So the next chapter then is cybersecurity for AI, right? Now, this is one of the mandates of the European Union, among others, about the use of AI. That AI systems must be trustworthy. What does that really mean? Well, if you look at this figure here, trustworthy AI means that it has to be reliable, it has to be resilient, and we did touch upon the concept of resilience. I will come back to that, hopefully. I will remember to come back to that before the end of the talk today. And it has to be responsible. So obviously, the interest here is under resilience, and under resilience, the three attributes are to be safe, to be secure, and to be private. And again, I will not talk, of course, about privacy, but it's about safety and about security, and I will say more about security. So safe, what does it mean? It means doing no harm to living beings or the environment, and Peter covered aspects of this very well in his talk, by the way. Secure, well, it means that it has to be resilient with respect to the CIA triad, confidentiality, integrity, availability, to malicious activities and adversarial attacks. By the way, this is just a slight deviation. If we talk about critical systems, which usually are industrial control systems, the CIA triad is not enough. We need to extend the model beyond confidentiality, integrity, and availability. But as I said, this is a side note. And just to clarify things, because there are many that confuse the terms risk, attack, vulnerability, and so on, attack is the purposeful manipulation of an AI system with the end goal of causing it to malfunction in some way. And later on, we will see some of these possible malfunctions. Now, what can happen? I guess, do you know this example? No, but you can imagine. This, obviously, it's a cat, right? Fine. And when it was, the image was subjected to one of the well-known ML toolboxes, right? The answer was with an 88% confidence that this is indeed a tabby cat, right? Do you think that this is any different? Anyone that doesn't believe that this is a tabby cat? Well, yeah, one of my students once said, yeah, it's a dog. Yeah, but this was only fun. Well, unfortunately, the toolbox wouldn't agree with you. The result was that this is with a 99% confidence that it is guacamole. So what has happened? Well, obviously what has happened is what we call an adversarial perturbation between the two, right? So the original image was perturbed in a specific way that resulted in an image which is imperceivably similar to the original one, to the human eye, but it fooled the machine learning system. By the way, this is where the example comes from. It's one of the important papers in the literature about this by Adi Shamir and colleagues. Now, is this really interesting, or is it just Adi Shamir playing around with the math of images? Well, actually, what you see on the left side here, this is the number, the cumulative number of papers that have appeared in the literature about adversarial examples in the past years. So you can see that the interest is really, really very high. But remember this when we discuss a little bit later about the feasibility and the realism of such attacks. Obviously, academia, we tend to create problems and then to solve them, right? This is good for writing papers, but the real world may be a little bit different. But it does show that there is a trend in this research direction, right? And what you see on the right-hand side is a classification of, well, not exactly the same set of publications, but a different one, perhaps, on what these adversarial examples were about. And the majority here happened to be about visual recognition. This is, again, normal because image processing is one of the flourishing areas of application of ML, but spam filtering and intrusion detection were not low. And of course, there is this multi-purpose category which has everything in there, or any other business, whatever you prefer. Now, if we just take it a little bit further, any ML system is practically a system that can be abstractly represented by an input, by a processing unit, and by the output. So attacks of this kind can be launched against the input part, or they can be launched against the processing part of it. Of course, they can be launched against the output part as well, but this is not really interesting because this could happen in any type of system. So if we just discuss a little bit about those attacks against the input part of the system, there is a classification which I find quite useful. As you can see, this goes along two axes. So one axis is the perceivability to the human of the attack. So up here we have perceivable attacks. We can identify visually that something is wrong here, but here we cannot. And on the other hand, we have digital attacks versus physical attacks. And there are several examples here. Some of them are quite inspiring, I would say. But again, I have to wait. It's coming. I hope. Maybe I shouldn't be using the laser pointer. Yeah, it came up. Okay, good. So this is a visible attack, and maybe this is something worth looking at, Peter. I don't know whether you can see it, but this is a stop sign, and somebody had stuck stickers on selected places, and then this was classified as green light. So this is a hazard, like the ones that you said, cyber hazard. Maybe,
Yes,
maybe.
pointed.
Yeah, okay. Yes. Yes. Yeah, over here. But of course, it won't be visible in for the online ones, but it doesn't. Yeah. But okay. So this is one case. Does it go?
What was the classified the second time?
Green light. That can be a bit, catastrophic, maybe. Okay. And then there are other examples of this classification, but it still refuses to continue.
Every time I see the laser pointer, my heart like skips a bit.
Okay,
Because
yes.
I think it's gonna crash
We should stop it. Yes. Okay. No? Did it come up? It did. Okay. Well, this is an invisible attack because it's only adding noise to the original image. You cannot perceive that something has changed, but the panda has become a monkey. And then other examples of physical attacks. Well, of course, again, the stop sign, the turtle that has been painted, that has been classified as a rifle. Yes, and so on and so forth. And finally, this one here, which is a digital attack, and definitely this cannot be Alice as wrongly classified. So just some examples of input attacks. Then, of course, we can go into the processing unit, and here what we have, one can attack the data set, one can attack the algorithm, or one can attack the model. And a proposed classification here by a group of people at Edinburgh, Napier University, that we have collaboration with, is this. So for those of you in the room, the focus is, of course, here. So we speak about poisoning attacks and evasion attacks. The former pertain to the training phase, the latter pertain to the testing phase, and this is how all this can work. And finally, this is another interesting attack again, or the result of the attack. And the same group in the same publication have come up with a classification of attacks against machine learning systems. They looked at quite a large body of literature and came up with this proposal that breaks down the attacks into the preparation phase and the manifestation phase. And here you can see that the taxonomy or the ontology identifies the knowledge of the attacker, the algorithm, how it operates, whether game theory is being used or not. Yes, game theory has been used to design such attacks. The specificity of the attack, whether it is an indiscriminate one or a targeted one, and then the attack type, and finally operating the attack mode, whether it requires collusion or not collusion. As I said, shouldn't go into detail for that. And again, this is something that I will very quickly pass, because these are different attacker capabilities and there are different attacker goals. I'm only using those to show you this slide, because one might wonder, is it so easy to launch an attack, to design and launch an attack like that against a machine learning system? Well, it turns out that it's not that easy. It may be in several cases, but if you look at the capability of the attacker Well, of course, if you have a white box attack where we assume that the attacker knows practically everything, he or she knows the algorithm, knows the model, knows the everything, right? Then, of course, it's relatively easy to launch an attack like that, particularly if the attacker just wants to reduce the confidence in the classification, which is an easy thing to do. But as the complexity increases towards more targeted attacks and the capabilities of the attacker decrease, then you can see, of course, this is not linear. No one knows how exactly this could go, but the trend is that the difficulty increases with decreasing capability of the attacker and the increasing complexity of the attack. Now, moving on to one of my favorite parts of it, which is the use of machine learning for network intrusion detection systems. It also applies to host-based intrusion detection systems, but this particular figure has been taken from a paper that was discussing needs. And again, the question here is this. As I said, there are many papers that demonstrate how attacks against network intrusion detection systems can be designed. But until very recently, as you can see, this is a publication in 2022, and there is another one which has not yet been published, not by the same authors, but I have happened to review for a conference, and I know that it will be accepted. So I can, even though I don't know the authors, because it was a double-blind reviewing system, but still I will give you some of the result there. So no one had looked upon, to answer the question, fine, but is it feasible to design and launch an attack like this against a NIDS or a HIDS? And furthermore, is it realistic? So to cut a long story short, it's neither feasible in many cases nor realistic. And there is a very good reason for that. When it comes to images, there are practically no constraints within the structure of an image. So you can design an attack that will change the image in any way without violating any constraints. But if you try to launch an attack against an intrusion detection system where the data are very much structured, and in the feature space you have constraints between the different features. An example is that the payload cannot be larger than something, right? Just a very simple example. So this would mean that if you wanted to launch an attack against the machine learning system looking at this data, this would undergo the same constraints as the data themselves. And this has not been the case. So in fact, if you look at this column over here, which is the third from right, for those of you online, you will see.
I think we can use the laser pointer now.
No, no. So I'm pointing at the third column from the right. You will see that all these are publications about adversarial attacks against machine learning based needs. Right? Constraints have not been verified in most of them, which means that. So all this doesn't apply to the real world. Very few of these described attacks can apply to the real world. Okay, but there is something else as well, and coming back to the AI winter, right? Well, we tend to use AI, machine learning these days for almost everything, believing that it's better than what we've been doing up till now. But it turns out that this is not always the case. This is a paper that appeared in the last DESSERT' last September. The authors did a very simple thing. Actually, the title of the paper is simple, but this is an acronym. I won't bother you with what it is. But they asked the following question. Let's look at the literature using machine learning-based intrusion detection for industrial control systems. And let's see what results we would be getting if we applied simple statistical threshold algorithms on the same data sets. Imagine what? Oh,
This is one.
the statistics won. Yes. The statistics won.
So
In
it's
most of the
statistical
cases.
to make another winter break.
So, well, that's why I'm asking, is it always better? No. I could also argue, everyone today uses blockchain. Do we have to use blockchain? Is it always the best solution? Well, I don't really think so. These are nice technologies, but we should be careful with when we use them because there might be something better.
The same is debate, but it's not useful for any.
Exactly. Absolutely. Absolutely. Again, for academia, perfect. You write papers. We write papers, right?
To make paper.
Yeah. But okay. Final. Is there anything we can do? Yes, of course. And there is a lot of literature on defensive strategies. But again, I will come back to this point that all these strategies are specific for specific attacks. And it's no good doing something that will protect a system against a specific attack, and then it will leave it undefended for all kinds of other attacks. And as I said, in most cases, when you combine defensive strategies like this, the end result is not better than if you had nothing there or if you had a few of them there. So, any way to go forward? Well, I will just only give you one point here because I have to conclude. First of all, machine learning is only one part of a system. And I believe that we should be looking at the system. That's point number one, not just parts of it. And if we do that, then we need to have a holistic approach that will include people, technology. Technology is ML, but other technologies as well, right? And processes. And one way of doing it, of course, is by using the NIST cybersecurity framework. I happen to believe this is a good way of addressing these problems. And then looking at the time, unfortunately, machine learning works by learning patterns. We rely on data, but they are liable to break easily. The third bullet, because I already commented on the second one, goes to the black box nature. This is the explainability. We know that we can combine explainable AI, which doesn't have good accuracy, with non-explainable AI, which has good accuracy. But putting them together, again, is a challenge, and that doesn't mean that it cannot be attacked. But the major point here is that the attacks that have been made possible, they're not due to weaknesses. It's not a weak design of a system. There are structural issues there that need to be taken care of. In the image classification problem, what happens is that actually a few pixels can be moved below the hyperplane that separates the two regions of decision, and that's it. This is not a weakness. It's a structural problem. Then, is it a threat? Yes, it is. Poor performance in intrusion detection at least has been demonstrated, but several of those models that have been proposed are unfeasible or unrealistic. But it doesn't mean that we cannot use and we should not use ML and some of these conclusions to other detection problems, for example, phishing, malware detection, and so on. In fact, the first time I used machine learning for intrusion detection was 30 years ago. We developed a neural network within the context of a European project for what was then called the integrated broadband communication networks. This was the buzzword of the commission at the time for what we now know was networks. It didn't work for several reasons. But then, of course, we have used it. Also, my team has used it for malware classification. We used it very recently for detecting anomalies in the NMEA protocol. This is a communication protocol, network communication protocol, shipboard for ships. And we found that we shouldn't use it. We reverted to the statistics again, and so on. But there are applications there, right? So when we talk about mission-critical systems, we should be careful enough not to introduce vulnerabilities because of the use of AI in these systems. So what we need to do is to improve our understanding of how the two domains interconnect. This doesn't mean that we need experts that will be experts in both domains. We need experts from both domains to work together, and we are doing that at NTNU, fortunately, and to, of course, leverage this understanding to develop methods and tools so that we can efficiently address all these challenges. So it's all about collaboration. Thank you very much.
One small question, and it's more of a comment, not a
Yeah, sure.
question. But how much can we use and depend on AI systems to defend our structures? Because AI will need to feed some data. That data already exists. Nobody knew a DDoS attack before it existed. Nobody knew an anonymous attack before it existed.
Sure.
All those stuff. So we cannot be too dependent on AI because it cannot innovate. AI cannot innovate. It cannot find a solution to something brand new, to something that hasn't been introduced to it, so it can learn, right?
Well, actually, machine learning claims, and it's a valid claim, that it can identify unknown attacks, right? So if we have an intrusion detection system, ML-based, that has been trained on a set of attacks, right? Then, at least in the laboratory, we can demonstrate that it can also detect an attack that it has not seen before. But mind you, it's only in the laboratory.
To detect the anomaly of the system.
It can detect an attack. Well, it cannot tell you that it is an attack, but it can tell you that it is an anomaly, and therefore something, exactly.
Yes, Professor.
Thank you very much for your presentation. It was extremely interesting talk. My question is related to traditional security protection based on defense in depth.
Yes.
Approach. What your opinion? Is it possible to build protection system based on AI defense in depth? I mean, AI as a field.
Yeah. Yeah.
Similar in this classical.
Yes. Yeah, you can say this, but yeah, I think, well, it depends on the layer, and we've seen applications of different machine learning and AI technology at different layers of defense in depth. But I'm not sure that this can be applied to all the layers of a defense in depth model. But just inspired by your question, what I think is also important is this. In, let's say, 20 years ago, our security paradigm was that we should keep our systems secure by protecting them against the bad guys, right? But then, when communication technologies were integrated with information technologies and the systems opened up, so the computing paradigm changed. Our paradigm changed as well. And the emphasis was not so much on protection. It remained on protection, but there was an additional emphasis on detection. Why was this? Well, because the basic assumption that we could keep our systems relatively well protected and therefore they couldn't be attacked was not valid anymore. And we started assuming that even though we may be well protecting them, like, for example, defense in depth, right? Still, we would be attacked. And therefore, we would need to have procedures in place so that we could detect the attack. But in the past few years, one of the stimuli for what I will say have been the attacks against the Ukraine Oblenergos in 2015 and 2016, right? We now know that we will not only be attacked, but we will be successfully attacked, which means that now there is an additional focus. Not only protect, not only detect, but also respond and recover. So, and this is where brings resilience into the discussion, right? So,
It's real resilience.
yes. So maybe, I don't know whether I answered your question about the defense in depth and the AI, but I did take it as a trigger to comment a little bit
Yes, my
further.
question is based on my experience in safety.
Right,
Yeah,
yes,
where
of course.
atmosphere is the main.
Absolutely.
challenge.
Absolutely, yes, you're absolutely right. And of course, we have borrowed the defense in depth strategy in cybersecurity from safety, right? But there is a fundamental difference. In safety, we assume that there will be hazards, but this will not be coordinated. They will not be coordinated. And this is a fundamental difference with cybersecurity, because in cybersecurity, many people ask, okay, why then don't you just use what we know from safety and port it to cybersecurity? Well, an accident is an accident, but a cyber attack is not something that is at one point in time. It's a coordinated action that possibly is not just one action, but it goes on and on and on, right? Yes. And this changes the model quite significantly. Yeah, Peter, you.
I'm probably will take it up.
Okay, good. Yeah, okay.
I wanted to make an observation that you again mentioned intrusion tolerance.
Yep.
Because intrusion tolerance seems a big deal, at least in my mind. This is tested in cybersecurity. You don't make any assumptions about who, how they're going to do that, what they're going to do, and yet this is successful under certain assumptions, of course. So, but
Have any questions, please? More questions? From
Maybe I
online?
should stop sharing here.
It's okay. Okay, we don't have more questions. Thank you very much.
Okay,
Thank you very much, Professor Katsika.
thank you.
We have now coffee break. We have a small shift that comes from